On the evening of July 10th, 2024, a piece of equipment about the size of a fire hydrant failed on a 230 kilovolt line in Northern Virginia. It was a lightning arrestor. Its job is to catch a surge and send it safely to ground. When one fails, it becomes the fault it was installed to prevent. The protection system did exactly what it was built to do. It opened the line. Then, because most faults on overhead lines are temporary, a branch, a bird, a flashover that clears itself, it closed the line again to find out whether the fault was still there. It was, so it opened again and closed again. Both ends of that line were set to try 3 times, and the timers at each end were staggered. What should have been 1 fault became 6, spread across 82 seconds. Every one of those 6 was cleared correctly in 42 to 66 thousandths of a second. Nothing broke, nothing was damaged, no operator made a mistake. And in those 82 seconds, about 1,500 megawatts of electrical demand vanished from the grid. Not a power station. Demand. 60 separate points of consumption across 25 substations in Loudoun County, Virginia, the densest concentration of data centers on Earth. Not one of them was disconnected by the utility. Every one of them left on its own. And here is the part that should stop you. When a grid loses generation, frequency falls. That is the signature every operator is trained on from the first day. That evening, frequency went up. One more thing about that night. It is the best documented event of its kind that has ever happened. Hold on to that. By the end of this film, it will matter more than anything else you hear. To understand why that is alarming rather than merely strange, you need one fact about the grid. Almost everything else in this film follows from it. The grid does not store anything. There is no tank, no reservoir sitting behind the wall socket. At every instant, the power generated across an entire continent must equal the power consumed, plus losses. Not on average, not over an hour, at every instant. Nobody achieves that by being careful. They achieve it by watching one number. Frequency. In North America, 60 cycles per second. If generation exceeds demand, the generators speed up and frequency rises. If demand exceeds it, they are dragged down and it falls. One number, readable everywhere on the system at once. It is held extraordinarily tightly. Across 5 years and 157 million measurements, the standard deviation on the eastern grid is 16 thousandths of a hertz, 300ths of 1%. To move it, you need scale. The eastern grid responds at about 2,673 megawatts per tenth of a hertz. Lose a large nuclear reactor, 1,000 megawatts, gone in an instant, and frequency moves 37 thousandths. That is the machine. Now put it back in Virginia. 1,500 megawatts of demand left in 82 seconds. The generation was still running. It had nowhere to go. So the needle went the other way, to 60.047 hertz, and voltage climbed to 7% above nominal. Operators spent that evening switching capacitor banks out of service, removing support from a grid that suddenly had too much. Why did they leave? Not because anything reached them. The faults were 230 kilovolt events on the transmission system, cleared in a 20th of a second. What reached the data centers was a voltage sag. The lights dipped. A facility that cannot tolerate a dip installs protection that watches for it. And a common design does not simply watch, it counts. 3 disturbances inside 1 minute, and the scheme decides the utility supply is unreliable. It transfers the facility to its own backup, and it stays there. Not for a second, not until the voltage recovers, until a human comes and puts it back. That is a sensible rule for one building. The building's owner is protecting equipment worth more than the power. But the reclosing sequence on that line produced 6 voltage depressions in 82 seconds. 3 was the threshold. The 60 load points did not decide independently to leave. They all met the same criterion at nearly the same moment because they were all watching the same line. Roughly 1,260 megawatts dropped out at the 3rd depression and did not come back for hours. The investigation that followed is careful about assigning blame, and so should we be. No standard was violated. The utility's protection was correct. The customer's protection was correct. Every device on the system performed to specification. The failure was that nobody had modeled what those 2 correct designs do to each other, at a scale where 60 buildings behave as one. This is what the phrase systems failure actually means, not a broken part, 2 working parts meeting. Here is why that matters more than a curiosity about which way a needle moved. Every grid in North America is planned around one number, the largest amount of generation it could suddenly lose. On the eastern grid, 3,875 megawatts. In Texas, 2,805. Reserves are sized to it. Operators spend their careers training for it. There is no equivalent number for load. Nobody ever had to plan for demand vanishing because demand did not do that. Factories ramp down over hours. Cities cool overnight. Demand was the one thing on the system that behaved slowly. That is no longer true, and it stopped being true faster than anyone measured. A single facility in Memphis swings between 35 and 70 megawatts inside a minute, as training jobs start and stop. Another North American data center went from 450 megawatts to 40 in 36 seconds, sat there for 4 hours and came back. The thing that behaved slowly now moves faster than a power station can. The organization responsible for reliability across North America noticed. What happened next is worth watching closely, because the shape of it tells you more than any single document. August 2024, a task force is formed. February 2025, a resolution from the board. July, a white paper describing the risk. September, a Level 2 alert, a formal instruction to industry to report back. March 2026, a finding that the existing reliability standards are inadequate for this class of load. April, draft criteria to create an entirely new category of registered entity for facilities that compute. May 2026, a Level 3 essential action alert, the highest severity that organization issues and one it rarely uses. 7 required actions, responses due within months. In under 2 years, a regulator went from forming a committee to invoking its most serious instrument. That is fast for any institution. And here is the sentence that has to sit underneath all of it. An essential action is not a reliability standard. It carries no penalties. Meanwhile, in February 2025, the same thing happened again in the same place, larger, about 1,800 megawatts, across Loudoun and Fairfax counties. There is no published incident review for that one. So the record is this. The largest event of its kind was documented in detail. The larger event that followed it was mentioned once, in testimony. And the strongest available response is an instruction that nobody can be fined for ignoring. You would expect the next question to be simple. How much more of this load is coming? There are 3 serious published answers for the United States in 2030, and they do not agree. A national laboratory puts data center consumption at 649 terawatt-hours, with an uncertainty band running from 521 to 843. An International Energy Agency puts it around 430. An industry research institute gives a range of 380 to 790. Highest over lowest is a factor of 2.2. For the same country in the same year, from organizations that all read each other's work. But the widest gap is not between them. It is inside one of them. That industry institute's own projections are about 60% higher than the numbers it published 2 years earlier. Not because the world changed by 60%, because its assumptions did. And the same laboratory that published one estimate in 2024 replaced it entirely in 2026. Now hold two things at once, because the honest version of this story requires both. The growth is real. On the Reliability Organization's own forecast, data centers account for about 1/3 of total United States electricity load growth to 2030. 1/3 is enormous. 1/3 is also not all of it. Everything else, electric vehicles, manufacturing, air conditioning, ordinary demand, grows by more than 900 terawatt-hours in the same period. Globally, data centers are under 10% of demand growth. The load is coming. Nobody can tell you how much. If the demand is uncertain, what about the supply? Here the numbers look magnificent. At the end of 2025, more than 2,060 gigawatts of generation and storage were actively waiting to connect to the American grid. For scale, the entire United States generating fleet is about 1,300 gigawatts. There is, apparently, more than 1.5 times the existing grid queuing up to join it. 549 gigawatts of that has already signed or drafted an interconnection agreement and is simply not operating yet. So the obvious conclusion is that the supply problem is solved, and the only issue is paperwork. Now the measurement that changes the meaning of every number in that paragraph. Of all the capacity that entered American interconnection queues between 2000 and 2020, the share that had actually reached commercial operation by the end of 2025 is 13%. 75% was withdrawn. Median time from request to operation for projects finishing today is over 5 years. A queue is not a pipeline. It is a lottery ticket that costs almost nothing to buy. You can watch the same effect from orbit. An energy agency tracked 21 announced artificial intelligence campuses in the United States, each one between 600 megawatts and 5 gigawatts. Their floor space tripled in 18 months, the fastest construction that industry has ever done. Cumulative delivered capacity across all 21, just over 6 gigawatts, against announcements that plausibly sum above 40. So the announcements are not the supply. Fine. Stop listening to what is promised and go look at what is actually standing in the ground. Now turn the problem over, because a grid that cannot store power has a second failure mode, and it is the opposite one. Sometimes there is too much. In 2025, the California system operator curtailed 3,766 gigawatt-hours of wind and solar, power that existed, that cost nothing to produce, and that was deliberately not taken. The popular explanation is oversupply, too much solar at midday, nowhere to put it. The operator's own data says otherwise. 92% of curtailed energy was classed as local, transmission congestion, not a system with too much power, a system that could not move it out of where it was. Which brings us to the strangest number in electricity markets, the negative price. Generators routinely pay to keep running, and it is not irrational. A wind or solar plant can earn a federal production credit worth about $30 a megawatt hour, closer to $38 before tax, but only for power actually produced. In some markets, a renewable certificate adds up to $40 more. So the operator's own market monitor reports, year after year, that a rising share of capacity is offered at or below zero. In Texas, about a quarter in 2022, 35% by 2025. and they collide with plants that physically cannot get out of the way. In the largest American market, 53% of all megawatts offered day-ahead sit at or below their minimum output and cannot be turned down at all. 2/3 of wind and solar willing to be paid negative prices. Half the fleet unable to move. That is not a market failure. That is the whole mechanism. Everyone has the same answer to everything you have just heard: batteries. The build is genuinely extraordinary. In June 2026, the United States had about 52 gigawatts of utility-scale battery power and 142 gigawatt-hours of battery energy. 5 years earlier, it was under 5 gigawatts. Now put that against the demand it is meant to serve. Measured peak demand across the lower 48 states is about 760 gigawatts. The battery fleet's energy divided by that peak is 11 minutes. But that comparison flatters it, and it is worth being precise about why. 11 minutes assumes the fleet could serve the entire country. It cannot. Its power rating covers 6.8% of peak demand. The honest statement is that American batteries could supply about 1/15 of the country for a couple of hours, not the whole country for 11 minutes. There is a second belief here that the data does not support. Batteries are said to be getting longer, moving from 2 hours toward 4. The national average duration has been flat at between 2.7 and 2.9 hours for 7 consecutive years. The average is hiding something. Texas built a fleet averaging 1.6 hours for fast response in the seconds after a disturbance. California built one averaging 3.4 to move energy from afternoon to evening. 2 different machines, 2 different jobs, 1 misleading national number. And the Texas grid operator, accrediting what it can count on at peak, gives a battery of 1 hour or less 36% credit for its nameplate. There is a technology that does what batteries cannot. It holds about 80% of all the stored energy in the United States at a median duration of 12 hours. Pumped storage, water lifted uphill when power is cheap, released downhill when it is not. A century-old, unglamorous, and by far the largest battery America has. Here is when it was built. 16% in the 1960s, 48% in the 1970s, 22% in the 80s. Almost 86% of the entire national fleet entered service between 1960 and 1989. In the 2010s, the United States added 0 megawatts of pumped storage. In the 2020s, so far 0. The newest plant in the country entered service in September 2002, and the Army Corps of Engineers built it. One merchant plant was built this century, 42 megawatts in California, opened in 2012. It was retired in November 2024. Meanwhile, the paperwork is thriving. 47.5 gigawatts of pumped storage currently holds preliminary federal permits. That is 87% of every permitted megawatt in the national hydropower pipeline, reserved, studied, and non-existent. One project has held a full construction license since 2014 and has exhausted its extensions. And one number for how long these timelines really are. A plant that has been generating since 1972 applied to renew its license in April 2016. The license expired in 2018. The application is still pending. 10 years and 3 months for a plant that already exists. Everything so far points one direction, so it is worth stopping to make the strongest possible case for the other one properly, not as a courtesy. In February 2025, researchers at Duke University published an analysis that has since been cited in Congress, at federal regulators, and in state proceedings across the country. Their observation is simple, and once you see it, hard to unsee. A power system is built for its peak. It spends almost no time there. Across 22 balancing authorities covering 95% of American peak demand, the average load factor is 53%. The grid sits at roughly half its own capability, nearly all of the time. So they asked, how much new load could you add if that load agreed to step back on the rare occasions the system is genuinely tight? 98 gigawatts, about a tenth of national peak demand. The price is 177 hours a year of curtailment, 2% of the year, and it is shallower than it sounds. In 88% of those hours, at least half the new load keeps running. 17.5 gigawatts in the largest eastern market, 10 in Texas. An entirely separate team at Princeton, using a real utilities transmission model rather than aggregate data, found flexible data centers needing their own resources only 40 to 70 hours a year. Different method, same order of magnitude. This is a serious result. Nobody has published a rebuttal of the arithmetic, and none is coming because the arithmetic is right. The question is what it licenses you to say. The authors answer that themselves in their own limitations section, and they are blunt. Their model, they write, contains no transmission capacity, no ramping capability, no reserves. And therefore, their words, the results cannot be taken as an accurate estimate of the load that can be added to the system. They add that the figures should not be interpreted as showing that this load could be connected without expanding the grid. It is a measure of market potential. It is one number per region with no locations in it. It became a headline anyway. So test the promise directly, not the model, the record. December 2022, Winter Storm Elliott. The largest eastern grid called on its demand response program for 8,661 megawatts. Providers said they could deliver 7,400. 2,400 arrived. Across both days, the energy delivered was 27% of what the sellers had forecast. The official performance score for those days was 119% and 132 because 90% of enrolled sites were already shut. It was a holiday weekend. The factories closed before the phone rang. The program collected $86 million in performance bonuses. The cost of each megawatt hour of relief genuinely provided was $3,086. Measured properly, in 2025, the same program delivered between 49 and 72% of expectation across 6 events. None triggered a penalty. Texas found the same thing independently. Its emergency service has not been deployed since September 2023. And on that last deployment, the grid operator's own analysis found 60% of enrolled resources had already shut down before the instruction arrived, responding to price, not to the program. None of that is fraud. It is measurement. Every one of those numbers was published by the institution being measured, the market monitor on its own market, the grid operator on its own program. And they all measure the same thing. The distance between a number recorded at the moment of promising and a number recorded at the moment of delivery. Which brings us to the last document. In December 2025, the Texas grid operator published its official assessment of whether the state will have enough power. Beginning in the summer of 2027, that assessment assumes data centers are 100% curtailable, industrial load 85%, crypto mining 85%. Those assumptions carry the projected reserve margin from 18% to 28%. In the same document, the operator notes that the rules making any of it enforceable depend on regulatory proceedings that have not concluded. A reserve margin is a promise that the lights stay on. That one is doing arithmetic on a rule that does not exist yet. And now the counterweight, because a film that only points one direction is not describing a system, it is selling a mood. Things do get built. Batteries delivered about 90% of what was forecast last year. Gas turbines over-delivered. The projects at the front of the pipeline mostly arrive. The failure is not that America builds nothing. The failure is subtler and worse. The number everyone quotes is measured at the wrong end, at announcement, at registration, at enrollment. Almost never at delivery. One last thing, and then I will stop. In July 2026, it happened again. Same region, same kind of event. About 3 gigawatts of data center load disconnected at once, roughly 3% of demand on the largest grid in America, and the disturbance was visible on instruments from Washington to Chicago. Twice the size of the event this film opened with. I cannot tell you which day it was. Some accounts say the 22nd, some the 23rd. There is no incident review. There is no megawatt figure two organizations agree on. There is no published analysis of why those facilities left, or whether it was the same counting protection that took them out 2 years earlier. Remember what I asked you to hold on to. The event we opened with is the best documented of its kind that has ever happened. It is 2 years old. The largest one is 3 weeks old, and nobody has written it down yet. That is not a scandal, and nobody is hiding anything. Reports take time, and the people who write them are working right now. It is something quieter and harder to fix. The measuring runs slower than the building, and the gap is widening, which has a price, and it lands on people who never chose any of this. A reserve margin is a promise that the lights stay on. When it rests on an assumption nobody has tested, the failure does not arrive as a headline. It arrives as a dark house on the coldest morning of the year, and then as a line on an electricity bill for 20 years, paying for whatever had to be built in a hurry. The grid cannot store power. It cannot store a promise either.